In Chapter 10, we begin our study of alkenes. Recall that an alkene is a carbon-carbon bond that's composed of both a sigma and a pi bond. And we've already talked about the stability of alkenes, the most stable type of alkene being the tetrasubstituted down here, and the least stable would be no substitution, so this would just be ethene, the simplest alkene. You've already learned about cis and trans isomers of alkenes, but what you haven't learned about yet is a group like this, where you could not really say if this were cis or trans in nature. When you have an alkene with more than two groups on it, more than two R groups on it, you have to start using a different type of nomenclature. And so what we're going to do is bisect the alkene down the middle like I've shown with the red line, and then you're going to look at the right side separately from the left, and you're going to use what you learned when we did R and S designations, the Kohn-Ingold-Prelog rules, and you're going to give these a priority number, the groups. So let's start with the right side. This group here, the isopropyl group, is going to be a higher priority than the ethyl group on this side. So we're going to give isopropyl a number 1 and ethyl a number 2. On the other side, we use the rules and see that a propyl group is going to be a higher priority than a methyl group. So we do a 1 and a 2. And then what you're looking for is the orientation of the 1s relative to one another and the 2s relative to one another. So since the 1s are on opposite sides of the double bond and the 2s are on opposite sides of the double bond, this gets the designation E. So it's not a cis or trans, but we're going to call this an E isomer. On the other hand, if the 1s and the 2s were on the same side, so you see here I've moved the propyl group down and the methyl group up, this would be giving the designation Z, so we would call this the Z isomer. And you will incorporate these E and Z designations into the name of the alkene. We're not going to go into the specifics of the nomenclature at this moment, but just to give you an example, this would be the E isomer, how you would incorporate the E into the name, and the Z isomer. So it goes at the beginning in parentheses, kind of like you would for R or S or cis or trans. In terms of physical properties, alkenes and alkanes are rather similar. The melting points and boiling points would be rather comparable if you're comparing two of the approximately the same size, an alkane versus an alkene. The only intermolecular forces between them, of course, are going to be dispersion. However, if you have a cis versus a trans isomer, because of the slight difference in the %S character, recall that the sp3 to sp2 carbon-carbon bond is slightly polarized, and so you have a little bit of a net dipole overall with the cis isomer. In the trans, these cancel each other out, and so there's no net dipole. So you do have a very small net dipole with cis, and that's going to lead to a little bit of dipole-dipole interactions. And so the consequence of that is that a cis alkene is going to have a little bit higher boiling point than a trans alkene. For example, you can see that cis-2-butene boils at 3.7 degrees, while the trans boils at 0 degrees. However, when you look at the melting points, the cis-2-butene is at -139, while the trans is at -106. So this time the trans actually has the higher melting point. And the reason for that is because of the packing. So we haven't really talked much about melting points in this course yet, and that's intentional because it's not always easy to predict or compare melting points. The melting point very much depends on how the structure packs into a crystal, and so it has to do with crystal lattice energy and so on. And so sometimes it's not overly easy to predict. But you can see that comes up with the cis versus the trans. The trans can pack together much more tightly, so you get a more highly ordered crystal structure. and that's going to lead to a higher melting point. You can see how having a cis geometry within a larger molecule can affect the melting point of that molecule. So let's take a look at this plant oil, linoleic acid. Notice that there are two alkene moieties there that are both cis in nature. And this has a melting point of -5, and it's a liquid at room temperature. If you compare that to the completely saturated fatty acid, so this would be stearic acid, this has a melting point of 69 degrees and it's solid at room temperature. You can see that if the double bonds were changed from cis to trans, that this type of fatty acid would pack in a very similar way to just a fully saturated fatty acid. Sometimes during food processing, in order to change the consistency of some food product that's going to sit on the shelf, for example, a plant oil that has cis double bonds, like the one shown here, may undergo hydrogenation, which would mean that the food producer would add hydrogens across this double bond to make it saturated, to make it into an alkane instead of an alkene. And this is obviously going to raise the melting point by getting rid of the cis double bonds. The problem is during that process, a lot of times these trans fats are produced as a byproduct, and the trans fats happen to be toxic to the body because the enzymes in your body are not used to dealing with trans double bonds in fatty acids. Just a few notes about the nomenclature of alkenes. The main highlights are going to be that you have to choose a parent chain containing the double bond, and then you want to try to put that double bond on the lowest carbon possible, the lowest number, and then you need to add the -ene suffix. So if you go back to the E and Z slide, you can see an example of how I named those alkenes, and then definitely read the textbook for full details. You know how to make alkenes now, two different ways. Both are eliminations, but one's from an alkyl halide via E1 or E2, and one's from an alcohol via E1 or E2, and that's either under acidic conditions or using POCl3 and pyridine. In terms of the reactivity, alkenes obviously have pi electrons, and so those are nucleophilic, and the reactions that we're going to start looking at are going to be those pi electrons attacking some electrophilic species.